day everyone, I hope you're doing well. I'm Ral Ivan Machitar and I'll be your teacher for today's topic in biochemistry. Here are our learning outcomes for this short session. By the end of this video, you should be able to define what anomers are, distinguish between alpha and beta forms of monosaccharides, explain how cyclic structures form and the role of the anomeric carbon, and understanding the mutual rotation and why these forms matter in biochemistry. So let's begin by refreshing our memory a bit. Take a look at these three cyclic sugar structures, A, B, and C. Two of them are the same sugar, but one is different. Can you guess which ones represent the same sugar? If you answered A and C, you're correct. Both A and C are glucose, while B is galactose. Notice the difference between A and C. That small shift in the hydroxyl group on one carbon is exactly what we'll be talking about today, the concept of anomers. Monosaccharides, like glucose, don't stay in a straight chain form in water. They undergo a reaction where the carbonyl group reacts with the hydroxyl group on the same molecule. This creates a ring structure, more stable and dominant in aqueous solutions. Here, you can see a glucose folding into a ring. We call this the Haworth projection, and it's where anomers come into play. When the ring closes, a new chiral center forms at the anomeric carbon, the carbon that used to be the carbonyl group. Depending on where the hydroxyl group on this carbon points, we get two anomers. If the OH group on the anomeric carbon is opposite the CH2OH group, it's the alpha form. If it's on the same side, it's the beta form. So again, alpha anomer OH down and beta anomer OH up. This might seem like a small difference, but you'll see next, it's a big deal in biochemistry. In solution, these two forms don't stay put. They constantly interconvert through the open chain form in a process called mutual rotation. That's why freshly dissolved glucose rotates polarized light differently at first, then stabilizes over time. It's switching between alpha and beta forms. Now here's a quick question for you. Which linkage is found in cellulose that humans can't digest? Correct, beta linkage. Most humans lack the enzymes to break beta-1,4 linkages, which is why we can't digest cellulose, even though it's just made of glucose. To sum it up, monosaccharides like glucose form rings in water. When this happens, the position of the OH on the anomeric carbon creates two isomers, alpha and beta anomers. These forms differ only in how one group points, but that difference affects how the sugar behaves, reacts, and builds polysaccharides. Through mutual rotation, these forms shift back and forth, influencing things like taste, digestion, and energy storage. Now, it's your turn. Let's do a quick practice. Question 1. Which anomer of glucose has the OH pointing downward on the anomeric carbon? Correct, alpha. Question 2. What is the process called where an alpha and beta forms interconvert in solution? Right again, mutual rotation. For your activity, kindly answer the quiz linked below this video. You'll match sugar structures with the correct anomeric label. And don't worry, it's only a few items, so make sure to answer to test your mastery. And that wraps up our session on anomers of monosaccharides. I hope this helped you visualize and understand how small differences in structure can lead to big changes in function. If you have any questions or clarifications, feel free to comment or message us. This has been Ral Ivan Machitar. Thank you for watching and hope to see you in our next lesson.